Okay, our fantastic journey into the wonderful world of calculus continues. Today we're looking at the derivatives of trig functions and the derivatives of inverse trig functions. There's not a lot of deep insights to be found here. I've just got a couple of quick comments on them. Uh, yeah, I don't know. Let's just do it. So we're going to start off with section G here. These formulas are all in the data booklet. Some of them are on page 11, some are on page 12. So, you know, take a look at your book if you got one at home so you can spot them. As always, the chain rule applies. So this is the derivative of sine of x is cosine of x. So if I had the derivative of sine of, say, 2x, then that's going to equal 2 times the cosine of 2x. If I had the sine of e to the x, that's going to give me e to the x times cosine of e to the x, and so on. So just, be ready for the chain rule. We'll see some examples where that pops up. You know the chain rule's everywhere at this point, right? So whatever, nothing big. Yeah, let's just take a little quick visualization, just looking at sine and cosine for a second. So just to make sure that you can really see what's happening here and feel comfortable with it. So our red graph here is sine. Now, just focus on the x coordinates and the slopes at those points. So I'm right here, x is 0. What is the slope at that point? Well, all right, we got to estimate it, but if I told you the slope was exactly 1, would you believe me? I think so. That seems reasonable. And 1 is the y value of cosine. Wow. As we continue moving to the right along our sine curve, the slopes are still positive, but they are decreasing until right here we hit a slope of 0. So our tangent line's horizontal. And that corresponds, look, to the y value on cosine of 0. It started at 1, then we had positive y values that were decreasing until we got to 0. Back to sine, now our slopes are negative, 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 until right here at pi, we've got a slope of about negative 1. That's our y value of cosine. And then they're negative, negative, but increasing until we get to a slope of 0 again, and that corresponds to a y value of 0 there in cosine. I'm sorry if this is immediately obvious to you. I don't mean to bore you, but it's really important that we be able to think in these terms where we can look at one curve and imagine what the slopes of the tangent lines are along that curve so that we can figure out what the graph of the derivative of that function might look like. That's something we're going to actually really be focusing on in the next chapter. So we can see that sine and cosine and their negatives kind of form this neat little derivative cycle where if we take the derivative over and over and over again, we get back to where we started. And this is something we're going to talk about in the next section, higher derivatives. Just a sneak peek ahead, we would say that if cosine is the derivative of sine, then we would say that negative sine is the second derivative of sine. And we could say that negative cosine is the third derivative of sine. And we could say that sine is actually the fourth derivative of sine. I don't know why we would say that, but we could if we wanted to. So we've got that little 4 cycle. Of course, we know that e to the x is in a cycle of 1 with itself. Okay, so here's just 2 examples. Dealing with trig functions, we got a product rule over here on the left. We got a chain rule happening over here on the right. There's not a lot to say. We're just applying the rules in more and more complicated situations. So take a look, pause the video. We're going to move on. 2 more examples. Again, pause the video, make sure this makes sense to you. We got chain rule happening in both of these. Okay, before we move on, I just want to point out, we're going to be dealing with these all the time. So, you're going to have those memorized. These 3 down here, they show up much more rarely. So, don't feel like you need to commit those to memory. Just look them up in the book when you need them. But the top 3, gotta know them. Of course, if you're taking AP Calc, then you gotta know all of these. And actually, I should point out, in case you're trying to memorize these, there are some patterns here that we should take note of. So anytime we have a function and its co-function, the derivative of the function is going to be positive. The derivative of the co-function will be negative. So sine goes to positive. Cosine goes to negative. Tangent goes to positive. Cotangent has a negative. Secant, positive. Cosecant, negative. And then the structure of those derivatives is also kind of the same. So the sine and cosine pair, their derivatives are just another single sine or cosine, but flipped. The tangent goes to secant squared. Cotangent goes to cosecant squared, negative, of course. And then you can see secant goes to secant tangent. Cosecant goes to negative. Cosecant cotangent. So it's kind of like if you actually know uh, sine, tangent, and secant, you can kind of come up with what the other three are just by like thinking like, okay, I need to throw a negative in there and change the function to its co-function, and then you'll get the other three for free. And as always, the proofs to these, like you can look them up in the textbook, a bunch of them are in there. You can look them up online. We're not required to know how to prove any of these. We only need to know how to do polynomial derivatives through first principles. So I'm not going to go into the proofs of any of these formulas. I don't particularly find them that interesting. Section H is our inverse trig functions. And I'll be honest, I feel like we don't use these too often in the IB. They come up a lot when we do anti-differentiation. So when we start working backwards, you'll see a lot of, we'll call them integrals later on. You see a lot of integrals of this form, and we'll need to work backwards to figure out that it's arcsine or whatever. But like for doing derivatives, we'll practice a few of them right now, but otherwise, I would not anticipate that these show up too often. At any rate, the formulas are again in the formula book on page 12. These three formulas you are absolutely not required to know unless you're taking AP Calculus, which is why I include them here. Again, notice that there is a repeated structure across these 6 derivative functions. The derivative of a function and the derivative of its co-function are going to have the exact same setup. It's just that the co-function is going to have a negative in there. The other thing we got to point out about these three, however, is that we do have restricted domains. Recall that the domain of a derivative function is at most the domain of the original function. Arcsine and arccosine are defined from -1 to 1 inclusive. Our derivative functions are defined from -1 to 1, but not including -1 and 1, because we can't take the derivative at an endpoint. We've talked about that in a previous video, so we won't get into the details here. Fun fact about this topic, the textbook didn't even think it was worthwhile to put a single example in, so I guess I won't either. But you know what it's going to look like. It's going to have, the function will be arcsine of whatever, e to the tangent of x squared, and you're going to have to use a chain rule like 6 times or something and figure out a derivative. That's what it always is, right? So, you know, let's move on. All right, 2 last things to wrap up. First, this is another formula that you need to know for AP. You don't need to know it for IB. However, there was actually a problem a few years back where the IB had students work through some steps to derive this formula, and then they had to apply it to some complicated situation. So I think this is interesting enough to look at. So this says that if we have an inverse function and we want to take its derivative, that's going to be equal to 1 divided by the derivative of the original function evaluated at the inverse function. At first glance, that's a lot. So let's look at 2 examples, one of which is like really simple and one is just a little bit more complicated. Let's talk about e to the x. So if our original function is e to the x, we know the derivative of e to the x is e to the x. And we know that the inverse of e to the x is ln of x. Now let's suppose we want to figure out what is the derivative of that inverse. What is the derivative of ln of x? And we, for whatever reason, we don't know that it must be 1 over x. I don't know. We can use this formula. So we're going to get 1 divided by the derivative of the original function, which is our e to the x. So here we've got e to the, but it's not going to be e to the x, it's going to be e to the inverse function. So we put ln of x in there. And of course, e to the ln of x is just x, so this will simplify to 1 over x. Here's a slightly tougher one. So our original function is sine, our derivative is cosine, our inverse is inverse sine, and we want to know what is the derivative of inverse sine. So we're going to get 1 over the derivative, which is cosine, evaluated at the inverse. So it's cosine of inverse sine of x. Now that's not immediately obvious how they cancel out. We can work this out geometrically though. So we have inverse sine of x. That's an angle whose sine is x. So I got a right triangle up here. I've got an angle theta, and I want it to have a sine of x. And now I want the cosine of that angle, so I use the Pythagorean theorem to work out what this adjacent side is, and I got the square root of 1 minus x squared. Put that in to my expression down here, and we're going to get 1 over the square root of 1 minus x squared, and that is the derivative of arcsine. Last one I want to show you, when I teach trig to younger kids, one of the questions always is, why do we have to use radians? Why can't we just use degrees? And it's like, come on, you brat, you're just used to degrees for some arbitrary reason. There's nothing good about dividing a circle into 360 things when we could divide it into 2 pi things. But the one of the reasons I always give though is calculus really just does not work in degrees. So let's take a look at that here. Let's find the derivative of the sine function when it's in degrees instead of radians. So in order to do this, it can be helpful to use some new notation. So I'm going to use bold font to indicate that my function is in degrees rather than radians. So we can convert between regular sine and bold sine like so. So now the derivative of bold sine is going to be the derivative of this thing, which is going to be the derivative of cosine of that thing multiplied by the derivative of the inside, chain rule of course, but then we can convert back into bold cosine. And so rather than having this nice pattern of going from sine to cosine to negative sine to negative cosine and so on, we end up with, we're going to have a whole bunch of factors of pi's and 180s coming out every time we take a derivative. So it just gets ugly. So this is one reason why radians are better. That's the end of what I got to say here, people. There's formulas. They're in the data booklet. You should know them. Don't forget the chain rule. That's all.